Welcome everyone. I'm Alison from the Postgraduate Association. Here we are again with week 3 of a four-part series with Megan Lee. Today is Advanced Statistics 1. So Megan will be back next week to deliver the final workshop, Advanced Statistics 2. That'll be Wednesday, the 2nd of April. So I'll post a link for that. And just a reminder, we are recording. And I see that a lot of people have been viewing our recordings on the SCPA YouTube channel, which is really good. So you can just kind of go over at your own pace. And I'll post that link of the recording as well. And just a quick reminder that we encourage you to become a member of the Postgraduate Association. And in that way, we can keep all these workshops running for you all year. And if you look at our website, we also offer a range of support for postgrad students. So thanks very much for everyone for coming along. And it's all yours, Megan. Thanks. Thank you.
Thank you, Alison, so much. Before I get going on the content today, I always like to give the Southern Cross Postgraduate Association a shout out. I did my PhD at Southern Cross Uni. I finished in 22. And to be honest, the Southern Cross Postgraduate Association was one of the best things I ever did. Joining them, the Praxis conference is amazing. You get to network with lots of like-minded people who are going through the same thing as you. And also, if things get tough and the university isn't able to support you, the Southern Cross Postgraduate Association is one of the best supports for things like that. So if you haven't already, I would highly recommend joining the SCPA. It's amazing. I still have friends now that I made from the Southern Cross Postgraduate Association. We're all writing and working together still and still connected even years on. So I think it's 8 years since we all started. And we all finished. That's a really big testament to the SCPA. Every single one of us who was in the SCPA finished our PhD. Right, so welcome everybody to Advanced Statistics and SPSS 1. My name is Dr. Megan Lee. I'm an assistant professor at Bond University. I did my PhD at SCU in nutritional psychiatry. So anything to do with diet and mental health, that's me. But I also branch out into body image and particularly in the postpartum period as well. If you are interested in seeing the progress of somebody's journey from psychology honours through to PhD, through to becoming an academic, feel free to follow my socials. You can go back as far as you want. I did start my Instagram in particular during my honours, so you can see the whole journey. My website, Food Mood Doctor, has all of my stuff on there, conference presentations, publications, things like that, but it's also got all of the SCPA YouTube videos there. So if you are having trouble finding them, you can go to my website. They're also on there. And feel free to email me if you are in need of any statistics tutoring. SCPA does cover 1 or 2 tutoring sessions if you are in need of them. Let's go. So the last 2 weeks we've been looking, the first week was about getting your data from like a survey platform or from your experimental research into the SPSS platforms. We also looked at JASP, which is a free online version, very similar to the point and click environment of SPSS. I showed you that last week as well, so you can utilize that if you are having trouble getting SPSS through the uni. But it is a very similar layout and very similar to how we do this. So the first week we looked at getting your data actually into the software programs, how to clean the data, the things to look out for, the things that you need to do before you can actually even start looking at how the data works. Then last week we moved into descriptive statistics. So descriptive statistics is taking your population demographic details and looking at what your population looks like. So what is kind of like the average age, how many females and males were in your data set, what geographical location did they come from, and using statistics to give you averages and kind of a spread around that average to, and will always be the kind of first paragraph of your results section when you're describing what your data looks like as a whole. So that was last week. And then we moved into the two most simple statistical analyses to answer research questions. We looked at correlations, which we will cover briefly again today because they are the foundation of regression. And then we looked at t-test, which is looking at the averages between two groups. So if you do an experiment, you give one group a healthy diet and the other group an unhealthy diet, and then you test the depressive symptoms of both groups, and you see if the average depression is different from the healthy and the unhealthy group. That's a t-test. So they're the two foundational, most simple forms of data analysis. Today, we're going to move into the more advanced version of correlations. So regression is the big brother to correlations. Correlations examine relationships between variables, and they can tell us a lot. They can tell us the strength of that relationship. They can tell us what direction the relationship is, negative or positive, and it can tell us whether or not there is a relationship at all. Regression does a little bit more than that. As well as telling us the strength and direction of the relationship, it also tells us the prediction. So how much of the outcome variable can we align to the predictor variable? So in our diet and depression example, which we will continue using today because repetition helps with understanding the concepts, how much of depression is taken up by diet quality and how much is taken up by things that are not diet quality? That's basically what regression can do. And that gives you a percentage, which is really easy to understand. Now, there are three different forms of regression that we will look at today. Simple linear regression, when you have one predictor variable, say diet, which we are manipulating or looking at, and one outcome variable, so say depression, what we're trying to see the outcome in. So simple linear regression, one predictor, one outcome. Then we're going to move into multiple regression, which is when you have one predictor and one outcome, but you want to control for other factors that might be influencing the outcome. So say for depression, what are some other lifestyle factors that might impact depression that isn't diet quality? In the chat box, I'd like you to just have a think about what other factors there might be that influence depression that isn't diet. Sleep, sunlight, perfect, very good. What else? So they're two lifestyle factors that also could improve or increase or decrease depression. Exercise is amazing. Socioeconomic status is a good one. Social connection. Alison was listening last week. Very good. Social connection. What else? What other factors that aren't lifestyle factors might impact depression? Age, good. What else? Age is a good one, actually. There are certain age groups that suffer from depressive symptoms more than others. Hormones, life events, history, good, trauma, all these things, right? So we can, and what the strength of regression is that we can take a prediction and we can control for all of those other things that could be causing depression. And at the end, we can say something along the lines of, after controlling for sleep quality, sunlight exposure, age, gender, geographical location, and social connection, there was still a significant relationship between diet quality and depressive symptoms. So what that means is that we're not just looking at this relationship or these predictions, we're also saying, okay, we know there's all these other things that can predict depression. After we control for those, we still have this significant relationship between our predictor and our outcome. And that's the strength of regression. It's such a strong argument to have in a paper. Now, there are two different types of multiple regression. The first is where you put all of those, what we call covariating or confounding factors into the model altogether, because we don't know which ones are more important or influence depression more than others. Or there's what we call hierarchical regression, when we as researchers kind of know that there is a order to these things. So out of all of those lifestyle factors, which one do you think is the strongest predictor of depression that we just mentioned? Type it into the chat box. Which one of those, apart from diet quality, because that's our predictor that we're trying to measure, out of all of those covariant factors, which one do we think? Social connection. Good, Susan. Excellent. Every time we run any type of study on diet quality and depression, I always measure social connection. It's always the highest predictor of depressive symptoms. Right? Good. So we know from the literature and from past research that we've done that social connection is one of the highest predictors. We also know that sleep quality, sunlight, exposure, and physical exercise are all very high predictors of diet quality. But we're also interested in age and socioeconomic status and geographical location and marital status and gender, but we know that they're not as important as these lifestyle factors. So we could build a hierarchy of importance of these covariant factors into the model, and I'll show you how to do that later. So they're the three different types. Simple linear regression, where you have one predictor and one outcome. Multiple regression, when you have multiple predictors and one outcome, and hierarchical regression, when you know kind of what order of importance they fall into. Right, before we move on, I know I've been using this word predictor and outcome a lot. I want to make sure that everyone knows the definitions of these before we move on. So in the chat box, if you could tell me what the definition of a predictor is and what the definition of an outcome is. And then we'll use them in an example for correlations. Okay, good. So this is important. So if we go back to the previous recordings, if you haven't watched them, because it's really important that you understand the difference between the predictor and the outcome. So we've got some here. Predictor is the pre-event and the outcome is the after event. That's a really good way of looking at it, Susan, actually. Predictor is the independent variable and the outcome is the dependent variable. And that is true in experimental research when we're using t-tests and ANOVAs. But when we're doing things like relationships and predictions using correlation and regression, we're usually using data from surveys. And the terminology independent variable and dependent variable aren't quite correct, because an independent variable is the variable that the researcher is able to manipulate, and the dependent variable is the outcome of that manipulation. In a survey, we're not really manipulating the IV and to get the outcome in the DV. So that's why there's this different terminology. So we call it the predictor and the outcome. So the predictor is the one that we are changing or seeing the changes in the outcome. So a quick refresher on last week when we talked about correlations. So correlations are the little sister to regression. They are the foundations, so much so that you cannot do a regression unless you have a significant correlation between your variables. So the very first step in any regression analysis is to do a correlation matrix, and we'll do this soon, to see which variables are significant with your outcome variable. So that's really, really important. But the correlations can also tell us a lot about the relationships in our regression before we even get started on our regression. So, quick refresher, correlations, as you will see here, all of these little dots on the scatter plot are like, I like to imagine them, they're like people standing in a car park and you can see the top of their head. So each of the circles is the top of someone's head. Where the top of someone's head is where they intersect between the two variables. We can have a positive correlation if all of our little scatter dots, all of our people standing in the car park are trending in this way. It's a positive correlation. And this will be denoted by an R, or a Pearson's R value, that is positive. The closer to 1 that the positive correlation is, the stronger the relationship, and the closer to 0, the weaker the relationship. How strong does the correlation have to be to continue with the regression? Excellent question, Rian. It doesn't matter how strong the correlation is, as long as the p-value is less than 0.05. So as long as it's significant, you can continue with your regression. So strength does not matter. So your R value doesn't matter. So that's our positive correlation there. On our right side here, we have our negative correlation, where all the scatter dots of the people standing in the car park are trending the other way. This is a negative relationship, and the R value will be negative. So the closer to -1, the stronger the relationship, and the closer to 0, the weaker the relationship. As you can see here in the middle, this is a 0 correlation. There's no relationship. The lines aren't trending in one way or the other. They are very horizontal. Excellent. A positive correlation means as one variable goes up, the other variable goes up. And a negative correlation means as one variable goes up, the other variable goes down. So if we were talking about diet quality and depression, if we saw a positive correlation with an R that was positive, trending in this way, as diet quality goes up, depression goes up. If we see a negative relationship on the right-hand side here, as diet quality goes up, depressive symptoms go down. That's kind of what we want to see in my research. Not always though. Right, so that's the scatter plot. It's the graph. It's pretty simple to understand. Who can tell me here in this example, we've got a scatter plot of people standing in the car park with the tops of their heads showing their scores on nervousness and their scores on how many cups of coffee consumed. So this little guy standing here at the intersection of nervousness of 9 has had 3 cups of coffee. So that's why he's standing in that part of the car park. There's one person down the bottom here at 1 score of nervousness who's had 1 cup of coffee. That's their head in the car park. And there's a person standing at 6 cups of coffee, or just under 6, who's at 10 nervousness scores. So is this a positive or negative relationship? Brianne, would you need to do a correlation for your covariant control factors before your regression? Absolutely. You always do a correlation matrix first, and we'll run through this in a second. And or only the significant covariant factors go into the model. Very, very good. So this is a positive relationship. So as cups of coffee go up, what happens to nervousness? It increases. Good. And as you can see here, most of our participants standing in the car park are very close to kind of each other on this line. It looks like they'd be hugging around a line, except for the person who had 3 cups of coffee with not a score of 9 nervousness. They're kind of an outlier. But the rest of them are clustering around each other quite well. So that looks like it would be quite a strong relationship. So the closer they cluster together like that, the stronger the relationship, and the more spread out they are, like we saw in the example here of 0, the weaker the relationship. Good. Do we have any questions about correlation before we move on to regression? Okay, we shall move on. Here is the formula for regression. I don't typically like formulas, but this one really explains how a regression works. So I'm going to go through it really quickly for you to understand. So y hat equals b1x1 plus bo. That's our regression formula. Y hat is the predicted value of y. Y is our outcome variable at all times, and x is our predictor variable at all times. So what we're trying to do is we're trying to find the predicted value of our outcome variable. So y hat, b1 is the slope of the regression line. So how steep or how not steep the regression line is. And it relates to the amount of difference in the outcome variable associated with a 1 unit difference in the predictor variable. So this is going to make more sense in a second when I turn it into a real life example of diet and depression. Bo is the intercept, which is the predicted value of the outcome when the predictor equals 0. And x is the value of the predictor variable. So let's make that more real world. And the reason why I'm always doing diet and depression is because everybody eats and everybody has a brain, so it's a little bit relatable. And I'm always repeating the same example so that as we go along, the repetition is making it easier for you to understand these more complex concepts. So y hat is the predicted value of depressive symptoms. That's what we're trying to find when we're doing a regression from someone's diet quality. So that's our question, right? What is the association between diet quality and depressive symptoms? So we're trying to find the predicted value of depressive symptoms from somebody's diet quality. BI is the slope of the regression line, the amount of difference in depressive symptoms that are associated with a 1 unit difference in someone's diet quality. So if someone's diet quality goes up by 1, how much do their depressive symptoms go up or down? Bo is the intercept, or the predicted value of depression when diet is 0. So what Bo is the baseline of depression before we take diet quality into account. So before we start increasing or decreasing someone's diet quality, what is this sample's depressive symptom baseline? And then X is the value of diet quality for each participant. So if I say I have a diet quality score from my survey that we did, so we've surveyed participants we've done a food frequency questionnaire and given them a continuous diet quality score between 0 and 105. We've asked them questions about depressive symptoms, a continuous score between 0 and 60. We're trying to find out what my depressive symptom score is from the regression from my diet quality score. So say my diet quality score is from 0 to 105. I'm going to give myself a diet quality score of 80. I think that'd be about right. Got my calculator out so I can do this. So if I wanted to know what my depressive symptoms are, we'd find out what the slope of the regression line is, find out what the baseline depressive symptoms are, and add my predicted value of diet quality to the formula, and we would be able to predict what my depressive symptoms are. So this is what it looks like visually before we do the calculation. So exactly like what we see with the correlations, right? So this is like a scatter plot. We've taken all of the little heads out of the car park, but they're still there in the background. Everybody's little heads are in here. But for simplicity, I've just shown you what the line looks like. So this is the line of best fit through those scatter dots. Over here on the left-hand side, we have the baseline of depressive symptoms before we take diet quality into account. So if diet quality is 0, this is the baseline. It's called the intercept because it intercepts this vertical line. That's where everyone's baseline is. That's where we start from. Now, for every 1 unit increase in diet quality, which is across the bottom of the graph here, so we've got diet quality 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because the scale ranges between 0 and 105, it looks like this diet quality scale is in measurements of 10. So 10, 20, 30, 40, 50, 60, 70, 80, 90 to 105. For every 1 unit increase in diet quality, so as we go up this horizontal line by 1, depressive symptoms decrease by 0.24. So our slope of our line is negative 0.24. So this is our regression. Baseline plus whatever my diet quality score is, times whatever the slope is my depression score. So let's do that calculation. So if my diet quality score is 80 on here, so say I'm standing here in the scatter plot near the 8. Let's go back and put that into the calculation. So to find my depressive symptom score, we have to go BI, which was negative 0.24, times my diet quality score, which is 80, plus whatever the baseline of depression was before we accounted for diet quality, which was 31.84, equals. So my depressive symptom score then would be 12.64. So we've used regression to predict what my depressive symptoms would be if my diet quality was at 80. And we can do that across the entire data set by using regression. Any questions about how regression works theoretically before we move into how we look at it in the data analysis? No? Okay. So regression comes with several assumptions. It's the data analysis with the most assumptions, but most of them are done inside of the data analysis. So you just have to remember to scroll all the way to the bottom of the SPSS output to look at your assumptions before you start to interpret your analyses. So the first regression assumption is independence. Does anyone remember from our last workshop what the assumption of independence measures and how we assume independence in a data set? Yeah, good, Oscar. So in this circumstance, our participants have done a survey, usually, because regression and correlation is usually used in survey data. So independence is usually assumed that each participant only did the survey once and they did not influence other people's answers to the survey. So independence is usually met in the research design, so you don't have to worry too much about that. The next assumption is the reasonable ratio of cases and predictors. So you need to have a sample size that's large enough to give you a correct result. Now, we used to use lots of formulas to calculate the number of cases and the number of predictors, but now we have what's called G-Power. G-Power is a free download online sample size calculator. And all you have to do is type in to the click box that you're doing a linear multiple regression, fixed model R squared deviation from 0, that you are looking for a power analysis, which is a sample size analysis a priori, which means before you are collecting your data, you want to find out how many participants you need to ensure that you have power. We usually use an effect size of 0.15, which is moderate effect size. an alpha level of 0.00, because that is the significance level that we are using for our testing, and with a power of 0.80, which is about medium as well. Then you put in your number of predictors. So how many variables do you have in your model? This is obviously for a simple linear regression because there's only two, one predictor, one outcome variable. So you put both of your predictors in. And then over here at total sample size, it tells us that we need 68 participants to ensure power for our data. Now you must always do this before you start collecting data so you know how many. And I always inflate my number of participants that I need by 100 to 200 depending, because you will have data that you need to clean out, as you saw in the first workshop that we did. So that's G-Power. If you need any help with G-Power, just email me. I can send you the G-Power manual. It's quite simple to use once you know how. And then you don't have to stuff around with formulas for sample size. The next regression assumption is normality. We covered that last week. You want to make sure that your predictor and your outcome variables have a normal distribution. If they don't, there are transformations that you can do. You do a box and whisker plot to check for outliers. We're going to do all this in a live analysis in a moment, so you'll be able to see the box and whisker plot for itself. And then you want to see that there's a linear relationship on a scatter plot of all of those heads in the car park, that there is a line that you can put through that. If there is like a W shape of your scatter dots or a U shape, you can't do a linear regression. It's the biggest assumption of regression that we need our scatter plot to have a straight line. Whether that straight line is completely straight across, or whether it's positive or negative, it doesn't matter, as long as there's no W shape or U shape. That's really important. If there is, that's also answered your research question, because it just means there's something different to what you hypothesized is going on. We have an additional assumption that we did not look at last week. It's normality, linearity, and homoscedasticity of your residuals. So this is a little bit different because residuals are the errors in your data. So how far each participant is away from that line of best fit that we looked at, not between the two variables themselves. So those three assumptions are done inside the regression testing, and I'll show you how they work in a moment. And then we've got our independent errors. We use Durbin-Watson for that, also within the linear regression analysis. And any values that are between 1 and 3 are fine. Anything outside of 1 and 3 are cause for concern. Now, assumptions, if you've got 1 or 2 that are violated, usually regression is pretty robust to these, and you may not need to do a transformation of your data. But if all of your assumptions are out, normality's out, linearity's out, independent errors is out, then there's something wrong or different about your data set that you need to assess. And you always go to your supervisors and ask them their advice if that does happen. Right. So last week we analysed our correlations. So we're going to take that exact same test that we did, and we're just going to expand on it. So last week's research question was, is there a relationship between diet quality and depressive symptoms in plant-based dietary followers? This week, we're going to expand and we're going to look at the predictions of those relationships that we found. This is taken from a live data set that we used we collected in 2023. We're still writing this paper up because some really interesting things happened in the data, and we're trying to figure out the best way to write up what happened. Basically, the Indian population and the Australian population had different results. So we had to split the file, do 2 regressions, all this sort of stuff. But it's really interesting and cool, our findings. So it's actually very fun what happened. But we're going to use that today. We're not going to split it between geographical location. We're just going to do what happened overall. So our research question that we're using today for our regression is, does diet quality predict depressive symptoms after controlling for other demographic and lifestyle factors. So our regression or our correlation research question last week was, is there a relationship between depressive symptoms and diet quality? Great, that tells us something, but a research question for a regression can tell us so much more. How much of depression is actually taken up by diet quality as a percentage? And if we control for sleep quality, sunlight exposure, exercise, alcohol consumption, age, gender, marital status, does the relationship between diet quality and depressive symptoms still exist? Or is it there because of the relationship between another lifestyle factor and depression? So do we have any questions before we move into the SPSS data set? Yes, Ryan. Can you use the word predict if you haven't ascertained that the variables are correlated yet? Yes, you can, because it's your hypothesis or your research question. You can still ask that question. Does diet quality predict depressive symptoms? Even if you haven't done your correlations yet. Because they're always the first step of your data set, of your regression, but you won't know that when you are creating your hypotheses, your research questions up, when you're doing your introduction. So you can always use the word predict because it's always your question about the world. Good question. Right, so I'm just thinking of how I'm going to do this. I might actually just get into SPSS and run you through each of the sections. And I'll just quickly flick through the slides for the first bit that we're going to do. And then we'll get into that so that you know kind of what's coming up or what's happening. So first I'll show you a really cool trick that I only learned a few years ago about getting your SPSS output to format in APA 7. So you don't have to mess about with tables in Word and changing them. So this is a really good feature now. So both in charts and tables, your output can be shown in APA 7. So you can just copy and paste it directly into your reports now, which is amazing. So let's go. Regression in SPSS. You must always have a significant correlation between your variables to conduct a regression analysis. That means that every single variable, including your predictor and your covariant factors that you're interested in, must have a significant relationship with the outcome variable to go into a regression model. So we always begin with a correlation matrix. So first I'll show you how to make sure your output is in APA 7. Then I will show you how to produce a correlation matrix. And this is the APA 7 output, which is amazing. That's like hours of time saved from just learning about how to format that in the output. So we're going to do a correlation matrix of depression, diet quality, age, gender, marital status, BMI, sunlight exposure, and social connection. That's what we measured. There's some other variables here that we've measured, like education level, whether or not the participant's vegan or vegetarian. SQS is sleep quality. We didn't put that in. Maybe I will. We'll see. We'll produce the correlation matrix and we will see which variables are significant to go in the regression models and which are not. And then we'll start on our assumptions testing. So normality and outliers. We'll do linearity by conducting a scatter plot. And then inside of the regression analysis, we will do our 3 residual assumptions. And then we'll do a simple linear regression first of just depressive symptoms and diet quality before we move on to multiple regression. We'll just do a simple linear regression and I will explain the difference or the prediction between diet quality and depressive symptoms without controlling for any other factors. And then once we've done that, we'll do a multiple regression, which will be really interesting because this will show you what happens when you add more variables to the regression and how it changes what the argument is and why it's so important to do multiple regressions. Right, let's go. I'm going to stop sharing the PowerPoint and I'm going to start sharing the SPSS. Tell me when you see the SPSS output, please.
Yeah, we can see it.
Excellent, great. So first things first, let's have a look at how to get your SPSS into APA 7 format. Keeping in mind that once you get access to SPSS, you can rewatch the recording and pause me, fast forward me when I'm boring, rewind me when you want me to say something again, and follow this along whilst you're doing your own data. So please do utilize the recordings in that way, because I step through this, every single step is related to every regression. So first, let's go. Let's save ourselves hours of formatting time in Word and put our data output into APA 7. So we go Edit, Options, and in Options, we've got a tab called Pivot Tables. In Pivot Tables, we want to click on APA times Roman 12. There's also APA sans serif. If you are doing your thesis in sans serif APA rather than Times New Roman, click on that. So we click on whichever one you want. Adjust for labels and data for all tables and click OK. You can also make your charts in the chart tab in APA 7 format as well by clicking on this box here. APA for bar charts and scatter plots. Very good. And click OK. Now all of your output should be formatted in APA 7. Next, we are going to produce a correlation matrix because the very first step in a regression is to ensure that our variables are significantly related to the outcome variable. So in our example, does diet quality predict depressive symptoms after controlling for covariant factors, which is our outcome variable? Depressive symptoms, good. So in our data set, depressive symptoms is here. The label is CESD total for the Center of Epidemiological Studies of Depression scale. It's a total score. If you want to know how to do that total score, go back to last week and the week before's workshops where I showed how to create a total score. This scale ranges between 0 and 60. So all participants should fall between 0 and 60. Higher scores equal greater depressive symptoms. The cutoff is 16, I believe. I think that's written. Cutoff is 16. Sorry about that. What is the predictor variable? What is the variable that we are looking at to see the change in the outcome in our research question? Excellent, diet quality. Diet quality is here. It's the DST total, which is the dietary screening tool. Scores range between 0 and 105, with higher scores equaling greater diet quality. Great. And then we've got some other variables here of interest: gender, age, body mass index, which we used height and weight to calculate in a previous workshop. If you want to know how to do that, go back and watch that. We've got geographical location, we've got marital status, we've got education level, we've got whether or not our participants are vegan or vegetarian. That becomes important later on when we're looking at differences between groups. We're not doing that today. We're just looking at diet quality and depression overall. We've got sunlight exposure, we've got social connectedness, we've got sleep quality, we've got the DAS, which we haven't used, which is interesting. So I could go back and use the DAS in future publications and look at anxiety and stress as well as depression. And then I've got the IPAC, which is a physical activity score. I didn't really like it. It wasn't intuitive to use, so I'm looking for a different physical activity markups. In a research paper, would you have to justify why you have entered in each control variable? No. In your data cleaning, the only thing you have to report are any participants that you removed, how many missing values you have, things like that. Would you have to find literature to say BMI is related to depression? Yes. You can't just put a variable in because you're interested in it. It needs to kind of have a basis in the literature of being related. Very good question. Unless you're doing exploratory. Right, so this is the data view. Each of the rows is a participant and their scores on each of those variables. So our very top participant is male. They're 29 years old. They have a BMI of 22, which seems pretty normal. They're from Australia, Australasia. They're married. They've got a postgraduate education. They're a vegan. They get more than 30 minutes a day of sunlight. Their total score for CESD is 10. When you consider that's between 0 and 60, it's under the cutoff of 16. That's pretty good. The diet quality is 78, which seems pretty good when compared to 105. So let's go and produce a correlation matrix. So we've got, let me just have a look, 319 participants. So let's go and see what their diet quality and covariant factors look like in relationship to depression. So we go analyze, correlate, bivariate, because we're looking at the relationship between two. So diet quality and depression, gender and depression, age and depression, sleep quality and depression, it's always 2. Then we get a little pop-up box. Can everyone see the pop-up box? Yep, great. Now, a tip for you when you are producing a correlation matrix is to always put your outcome variable in first, because it makes it much easier to interpret the matrix. So in we go with depressive symptoms. We can also go over to the list of variables, and as you can see at the moment, they're listed as their variable labels. If you want them as the variable names, you can just right-click display variable names, and it makes it a little bit easier. So we've got diet quality in second because it's our predictor variable. So outcome variable first, predictor variable second, always in our correlation matrix, and then your other variables can go in whatever order you want. So we're interested in gender, we're interested in age, we're interested in BMI, maybe sunlight exposure, social connection, and maybe sleep quality. Let's have a look at those. We want to tick Spearman's because looking at Pearson's correlations is only relevant to the continuous variables. You want to look at the Spearman's relationship between the categorical variables and depression in this case. Click OK. Can we see the output? This is the next thing. I might have to reshare the output screen. So I'm pretty sure I will have to, so I'll do it anyway. There we go. Output screen. Here is our correlation matrix. Now, the reason that I told you to put CESD first is because that puts the outcome variable in the first column, which makes it so much easier to interpret, because we're only really interested at this stage in the relationship between our predictors and our covariant factors and the outcome variable, which will be in this first column. So if we have a look at the intersection of depression and diet quality, what is our Pearson's correlation value statistic? What is the R statistic? Negative 0.275. So does that mean we have a negative or a positive relationship between diet quality and depressive symptoms? Negative, which means what? As diet quality goes up, what happens to depression? It decreases. Good. That's in line with our hypothesis. Woohoo! What about the strength of our relationship? Remembering that the closer to 0, the weaker the relationship, the closer to 1 or -1, the stronger the relationship. What do we think about 0.275 as a strength of the relationship? It's weak. It's on the verge of weak to moderate. It's okay. Now, look below that at the significance level. So this is our p-value. What is the p-value statistic that is reported here for diet quality and depressive symptoms? It's significant. Great. Good, because it's less than 0.05. Excellent. So, although it looks like a weak relationship, it's still significant, and that's all we really care about at the moment to put it in our regression model. So let's look at the next variable, gender. What is the, and without looking at the R values, let's just look at the P values, because all we care about right now is whether or not these relationships are significant to go in the regression model. Is the P value for gender and depressive symptoms significant? Not significant. So there is no relationship between gender and depressive symptoms in this data set, which goes against the literature because they always say that women have more depressive symptoms. But I contest that because I actually believe that men just don't report as much as women do. And this kind of supports my hypotheses. That's going off track. What about age? Let's have a look at the significance level for age. Rian, does that mean gender doesn't go in the regression now? Yes, absolutely. Do not put gender into the regression model. So far, only diet quality. What about age? Is age significant? No. So there is no relationship between age and depressive symptoms. Also very different to the literature, which is interesting. But there's another reason for that in this data set. Our data set is quite old. Well, saying that, the average is younger than I am, but for when you look at these things, 36 is kind of the average age here. So maybe that's an age group that doesn't experience depressive symptoms as much. So that might be the reason. But it doesn't go in our regression model. What about BMI? This is interesting. Is BMI significant with depression? No. That's also very strange. And this is why writing up this report is really interesting, because there's all these things that are occurring. So it doesn't go in either. What about sunlight exposure? Is sunlight exposure significant? Yes, great. So it goes into our model. It goes into our regression model. What about social connection? Is it significant? Yes, so it goes in our model as well. let's just really quickly discuss the relationship between social connection and depressive symptoms. What is the R statistic in this case? What is the R statistic for social connection and depressive symptoms in this case? Negative 0.649, so negative 0.65. It's a bit blurry, sorry. Bloody SPSS. Yes. So, with a relationship of 0.65, is that strong, medium, or weak? We consider that the strength of the relationship, the closer to 1, the stronger the relationship. The closer to 0, the weaker the relationship. Strong, I agree. Anything kind of over 0.5 is actually considered to be quite a strong relationship. This is really strong, especially considering it's nearly double what diet quality is. It's also negative. So as social connection goes up, what happens to depressive symptoms? It decreases. Good. That's in line with our hypotheses. What about sleep quality? Is it significant with depressive symptoms? Yes. What's its R value? 0.7. Also strong. What's interesting about this? Is it positive or negative? Which means as sleep quality scores go up, what happens to depression? So as sleep quality goes up, depression increases. What? But if you have a look at the label that we've given to that and why it's so important to write these labels into when you're doing your data cleaning, it says sleep quality scale, scores range between 0 and 84. Higher scores indicate greater sleep problems. So it didn't seem right, but the scale is actually the opposite way to what we expect. So what this really says is as sleep problems go up, depression goes up. That makes more sense, right? Good. Right. So what I might do now is we might just have a pause, have a 5-minute break. We'll come back at like 5 past, and then we'll do assumptions testing for linear regression. We'll do a simple linear regression, and then we'll move into adding those control variables and seeing what the difference is when we run the 2 different regressions.
Okay.
Excellent. Thank you, Alison. Right, so we've done our correlation matrix and we have figured out which variables need to go into our regression models and which ones to remove. You can also, at this stage in your results, also report the non-significant findings. So gender, age, marital status were not significant predictors of depressive symptoms. And maybe in your discussion, have a little bit of a discussion about why this happened in your data set. If it's different or similar to the literature, that's also a finding, right? So non-significant findings doesn't mean you've done something wrong or your analysis hasn't worked. It tells you something else, something different. So we would go in and describe why this data set is showing something different or similar to the literature in that case. So the next thing we're going to do before we run our analysis is we're going to run our assumptions. So our assumption of independence has been met in our research design, so that is all fine. But before we go in, we do kind of want to look at normality, outliers, and linearity. So linearity is our most important one. So to do this, and usually to go along with our correlations, we want to have a look at the linear relationship between the predictor and the outcome variable. So we will go to graphs, scatter or dot, so we want a scatter plot. We want a simple scatter plot. Our simple scatter plot, we want to look at depressive symptoms, which is our outcome variable, so that will go on the y-axis, and diet quality, which will go on the x-axis because it's our predictor variable, and just click OK. Share the output screen. And down the bottom here, SPSS is just telling us that it's running the graph. So we're just waiting for SPSS to run the analysis. It's not that tricky, SPSS, to do a scatter plot. Come on. Here's our scatter plot of our depressive symptoms and diet quality, with diet quality along the bottom and depressive symptoms along the vertical. We can double click on this graph, and over here, select add fit line at total, close, and then in our output, did I close down the whole output just then? No. We have our line of best fit. Now, the line of best fit tells us some interesting things. So firstly, it tells us that we can put a straight line through our scatter plot. So our assumption of linearity has been met. But it also gives us a really good example of the relationship between diet quality and depressive symptoms. Now, we already know from our correlation matrix that it's a negative relationship, and we can see that because of the lines trending this way. They're also clustered quite far around this line of best fit. They're not hugging that line. So it shows that maybe the relationship's weakish, as we saw up the top. So it also not only tells us our assumption, it also gives us a graphical visual of what our relationship looks like, which is really cool. The next thing that we want to do is our normality and our outliers. So I'll stop sharing the output. We'll go back to the data set. And we will do our assumptions of normality. So we'll go to Analyze, Descriptive Statistics, Explore, and we'll explore the relationship between the dependent variable of depression and diet quality. And we want to have a look at plots, normality plots with tests. Unclick stem and leaf and click histograms of our plots, and that will show us our normality tests. Click OK. I'll reshare the output. And our output here is our normality and our outliers. So here we've got our depressive symptom descriptive statistics. So our mean's 14.28, which is underneath the cutoff of depressive symptoms. So overall, our data set is actually not really experiencing depressive symptoms. That's another finding that will go into our results, because that's very interesting. Dietary screening tool 64 is around about the mean of the data. Then our test of normality, we've got Kolmogorov, Smirnov, and Shapiro-Wilks. Now, remember what we talked about last week? We want our assumptions tests to be not significant, because a significant statistic for an assumptions test suggests we have a significant violation of our assumption. So for our assumption of normality, look at Shapiro-Wilks. Do we have significant or non-significant assumptions testing for diet quality and depression? Now, p-value for the assumption of normality, significant or not significant for both depression and diet quality in that box for Shapiro-Wilks. Significant. Good. So we have a significant violation of normality, according to Shapiro-Wilks. So let's just go down and check that with our histograms. So we can see here our CSD, or our depression scale, is positively skewed up the healthy end. So most of our participants fall between 0 and 12, which is under the depressive symptom cutoff. Now, knowing how depressive symptoms should look in the general population, only about 12% of people experience depressive symptoms. So we actually should see a positive skew in depression. If we had a normal distribution like we talked about last week in our assumptions testing, then most of our participants would be experiencing depressive symptoms and there would be something very wrong. So we expect to see a positive skew. So it still means that our data is a little bit, might not be ready for analysis. Our QQ plot kind of tells us the same thing. So if the dots are snaking around the line like this in an S format, it kind of shows non-normality. And our box and whisker plots show us here that we don't have any outliers though for depression. So an outlier is usually denoted by a little circle or a star saying that you've got an outlier that might be skewing the data. So we don't have any outliers to remove in this circumstance. Then we've got diet quality. Diet quality is negatively skewed because most of our participants are up here, up the high end or the healthy diet quality end. Now, this might be because our participants are vegan and vegetarian, so they might have really high diet quality because of that. But that's also a finding of this data. So as you go along, make sure that you think about what these are also telling you about your data set and what you could be guiding into your findings. So we've got kind of a negative skew on diet quality as well. The QQ plot's a bit snaky, so it's showing that it's probably not normal. And we've got one outlier here down the bottom end of diet quality. So someone with a very poor diet quality, number 151, we might want to go back to the data set, have a look at participant 151 and whether that we ascertain that that's a correct piece of data or not. So that's normality in our outliers. The next thing that we need to do is we need to do our assumptions of normality, linearity, and homoscedasticity of the residuals, but that happens inside of our regression. So the next step is to actually do our regression and make sure we remember to look at our assumptions in the regression before we interpret our analysis. So to begin with, we will just do a very simple linear regression with just diet quality and depressive symptoms, and then we'll move on and we'll add the controlling covariant factors next. So to do so, we want to analyze regression linear, because we have assumed the assumption of linearity. We want to put the dependent variable of depression in the dependent box and the predictor variable of diet quality into the independent variable box. And then we want to click on statistics and we want to see the model fit, how well the model fits to the data. We can look at our descriptive statistics again, but it's going to kind of tell us the same thing that we found in the correlations. We want to estimate our regression coefficients with confidence intervals at 95. We want collinearity diagnostics, and we want to see our Durbin and Watson assumption and any outliers. Continue. Then we also want to have a look at a plot. So click plots, of our predicted values of our outcome variable and our residuals of our outcome variable. And this will give us the assumptions of normality, linearity, and homoscedasticity of our residuals. So it's going to plot it on a scatter plot, almost identical to what we saw before, but the residuals or the errors in the data rather than the actual data itself. The output. And here we go. So one mistake I always make is starting to interpret my regression before I look at the assumptions. So always scroll all the way to the bottom of your data set, of your output, to look at your assumptions testing. And right at the bottom, we have our scatter plot that we created of our residuals. Now, could we put a straight line through these scatter plots? Rianne, I might have missed this, but would you have to do this for every variable? No. Just the predictor and the outcome variable. So can we put a straight line, do you think, through these dots on this scatter plot? Or are we seeing a W or a U shape in the scatters? If you want SPSS to do it for you, you just double click on it, add a fit line at total. What's the output? There it is. Ooh, that's interesting. There is a straight line there. It's pretty horizontal. Good. The next thing that you want to look at is homoscedasticity. So we look at that through the scatter plot. If you see a funnel shape like this or this, then the assumption of homoscedasticity or heteroscedasticity is violated. This is looks like a nice cloud. So number one, we can put a straight line through. Number two, we've got homoscedasticity. It's fine. There's no funnel shape. Then we go up, we have a look at normality of the residuals. So we've still got a little bit of snaking around the line of best fit. It's still highly positively skewed, but that's because the depressive symptom scores are positively skewed. So we would expect to see this. So you could either do a transformation or bootstrap if you wanted to, but I think the regression is quite robust to this problem of normality. So I would just continue with doing this and state in my results that there was a positive skew, it affected normality, there were no outliers, and you would expect to see a depression score to be positively skewed. And then that's justified, so it's fine. So let's go up and interpret our regression, our simple linear regression. Here we go. So here's our regression, our descriptive statistics, our mean and standard deviation, we've seen them already. Our correlations, we've seen them already. So it's negative 0.275 and it's significant. We've seen that already. Our model summary. Now this is the one that's really cool and exciting and tells us the percentage that diet quality takes up. Knowing that there is a weak relationship, I'm not sure we're going to see a lot of percentage. So our R squared value that you can see here is the percentage that diet quality takes up in depression. What we have to do to convert that to a percentage is times it by 100. So how much percent of depression is taken up by diet quality? If we take 0.076 and times it by 100, about 8%, 7 or 8%. Yeah, good, Brianne. which means that 93 to 92% of depression is taken up by other things. That's one thing that we know, but because we haven't put other things into the model, we don't know what those things are. Our Durbin and Watson is also 0.63, and it should be between 1 and 3, so we might also have a problem with independence of errors here. Putting that on top of the normality problem, we might want to bootstrap our data. This box in our regression is the ANOVA box. The ANOVA box tells us whether the entire model is significant or not. If it is significant, we move on to seeing what in the model is significant. If it is not significant, if the model is not significant, we do not move on. So that's the important step here. So is our p-value greater than or less than 0.05 for our ANOVA, for our model? It's significant, great. So there is still a significant prediction of diet quality in depressive symptoms. They take up 7% of the variance or the variability in depression, basically. So that's what we know so far from it. Now, in a simple linear regression with one predictor and one outcome variable, this coefficients box is not as useful as what it will be in a second when we put all the other covariant factors in. But the coefficients box tells us what in the model is significant. So the ANOVA box tells us whether the model overall is significant, and the coefficients box tells us what in the model is significant. And that becomes very important when you have more than one predictor. So here it tells us that our diet quality score is significant. We've seen that before with depressive symptoms, and that this beta tells us that as diet quality goes up by 1, our depressive symptoms go down by 0.23. So that unstandardized beta tells us in a raw score how much depressive symptoms will go down with a 1 score increase in diet quality. That's what that unstandardized beta tells us. So that's our simple linear regression. Let's see what happens when we put more variables into the model. So let's do a multiple regression. And why don't we make it hierarchical? So let's assume that we know what variables are more important than other variables. So what variables were significant? So we had, I have to go back to the matrix. Oh, or I even do this. Correlation. So the variables that were significant were diet quality, sunlight, social connection, and sleep quality. They were our 4 variables that were significant. Now, what's interesting is that they're all lifestyle factors. So I probably would put them all in the model at once together. But if there were any demographic variables like age, gender, marital status, I would put them in the model together before I put the lifestyle factors in. So when you're controlling for variables, you want to put the least important variables in a block first. Then you want to put the next set of important variables in the block next. And then you always build a block with your predictor variable by itself last. So you can see what the unique variability of diet quality is after you've controlled for those variables. So let's do that. analyze, regression, linear. Now, SPSS always remembers the options that you had before. So we always reset for a new data analysis. We're going to put depression into the dependent box. And for the first block, we are going to put all of our lifestyle factors in. We're going to put sunlight exposure. We're going to put in social connectedness. And we're going to put in sleep quality into a block. Then we're going to click this next button. That brings up our second block. In the second block, we want to put diet quality by itself so we can see what the unique prediction is of diet quality after we control for everything in that first block. Oops, I've taken her out. That's no good. Diet quality by itself. There we go. Good. Then we want to go into statistics and we want our model fit. We want our confidence intervals. We want R squared change. So R squared change is going to tell us how much R squared, which is the variability that we found in depressive symptoms as a percentage, how much that changes between the two blocks that we've created. We can do our descriptive statistics again. We want our part and partial correlations because they tell us the correlation between the unique predictors. Durbin and Watson, we already know that's out. Our case-wise diagnostics, our collinearity diagnostics, and our covariance matrix. Then we click on plots. We want to do our predicted values of depression with our error. And we want our histogram, normal probability plots as well. Then we would like to save our Mulholland-Obis distance and our Cook's distance. This is going to tell us if we have like multivariate outliers. So any outliers that are on more than one of the predictors. Options is fine. You can choose to bootstrap. I'm not going to do it this time, although we probably should because of the Durbin-Watson being out and the normality problems. But bootstrapping takes a long time in the system, so I won't do it just because of that. And click OK. And then I'll show you the app. Let's have a look what happened once we've added our multiple variables. So remember, always scrolling right down to the bottom to have a look at our scatter plots. Again, they're looking okay. So this is diet quality and depressive symptoms. We could put a straight line through that. There's no kind of funneling going on. It's spread out. This is depression and sleep quality, same thing. Straight line can go through there. There's no real funneling. Same with social connection. It's looking fine. Sunlight exposure looks okay. So that's all looking fine. Normality is looking excellent for the model now. Have a look at that. So adding the variables, the extra variables has changed our normality. It's made the model more normal, which is interesting. Let's go up the top and have a look at what actually happened in our regression. Again, descriptive statistics, the mean and standard deviation of each of your variables, we've already looked at. We've looked at a correlation matrix previously, so that's all fine. Here is our model summary box. So this is the very first box that's important. This box tells us the percentage of the variability in depressive symptoms. So model 1 contains sleep quality, sunlight exposure, and social connection. So model 1 are all of our lifestyle factors together and depressive symptoms. So what is our R square for model 1? So lifestyle factors and depressive symptoms without diet quality, what is our R squared value? 0.591. Good. So if we times that by 100, how much of the percentage of depressive symptoms is taken up by sleep quality, sunlight exposure, and social connection? 59%. Good. Good. Now, if we compare that to what we found in diet quality before, how much was diet quality taking up? 7%. So that's much higher. So maybe those lifestyle factors are playing a role in this relationship or this prediction. Our Durbin-Watson is now 1.44. So now we don't have problems with our independent errors either. So adding these lifestyle factors have improved the assumptions of our test, which is very interesting. Now let's have a look at diet quality. Model 2 is sleep quality, sunlight exposure, social connection, and diet quality and depressive symptoms. So what is our R squared for model 2, where we've added diet quality but included all the other lifestyle factors? 0.594. So what's our R squared change then? If you go along the line and look at R squared change, what's the R squared change between model 1 and model 2? How much has our R squared percentage changed? .002 or 0.2% each. So this is very different, right? All right, let's look at our ANOVA box before we start interpreting what's going on. The ANOVA box tells us whether the model is significant. So, is model 1 significant with our lifestyle factors? Yes. Is model 2, including diet quality, significant? Yes, it is. So, now that we know this, we know that model 1, the lifestyle factors with depressive symptoms, is significant, but we also know that including diet quality, the model is still significant. So this is where the coefficients box becomes really important. So the coefficients box tells us what in the model is significant. So in model 1, when we don't include diet quality, have a look at the significance column and can you tell me, is sunlight exposure significant? So the first variable in the model. Oh, 0.79, not below 0.05. So sunlight exposure doesn't seem to be a significant predictor when we're controlling for the other 2 lifestyle factors of sleep quality and social connection. So sunlight is out. What about social connection? Is it significant in the model? Yes, good. And sleep quality, is it significant in the model? Yes, good. So let's go down to model 2 where we've added diet quality. Is diet quality significant with depressive symptoms once it is added to the model? No. So it was significant when we didn't control for our other lifestyle factors. So if we only did a simple linear regression and reported it in our thesis, we would say there is a significant predictor of diet quality and depressive symptoms. 7% of the variability of depressive symptoms was taken up by diet quality. But now that we've controlled for other variables, we can now say when diet quality was added to the model, there was no significant relationship between diet quality and depressive symptoms. So what we think is happening here is that either sleep quality or social connection has removed the relationship between diet quality and depressive symptoms. But we don't know that fully. What we would do next is what we're going to do next week. We would run a mediation to see whether social connection explains all of the relationship that diet quality has in depression. So it's very interesting that we found this. And later on, when we split the data by Indian population and Australasian population, we actually found that this relationship doesn't exist here because the Indian population, there is no relationship between diet and depressive symptoms in the Indian population, but it is in the Australasian population. So that's why we're finding this weirdness. It's really cool. Good. And then we've got some collinearity diagnostics, which tells us whether we've got multicollinearity or whether we have multivariate outliers as well. Usually, if you look at Cook's distance, if its maximum is greater than 1, then some participants have outliers on more than one variable, but it's not above 1, so we don't have to worry about that. Right, so I'll field some questions if you have any, and then we'll go back to our PowerPoint and just have a look at what that looks like visually, what we've just done.
Megan?
Yeah.
Oh, good. I do have a question, but it's too long to type.
Okay.
Say if in block 2 I had lots of predictors, but between block 1 and block 2 the R change is not significant. Can I still go on and look at block 2 to see if some of those new predictors were significant, but just overall it wasn't?
Yeah, absolutely. You can also flip your regression around. So say if we found this and we're like, well, we know that there was a relationship between diet quality and depressive symptoms in a simple linear regression. How did it go askew in this one? Why is it now not? You could flip your regression around and put diet quality in the first block and then your lifestyle is in the second, and just see where it lost its significance.
Okay. Yeah, gotcha. And when you compare the predictors in block 2, if you wanted to just say, compare sleep quality with sunlight exposure as a predictor, would you use the standardized beta score to describe, to compare them, or what score would you use?
That's a really good question. So the standardized beta tells you in raw score format, as diet quality increases by 1 score, depressive symptoms goes down by this many.
Yeah.
The standardized beta just says the same thing in standard deviations. So as diet quality increases by 1 standard deviation, depression goes down by this many standard deviations. So in regression, we usually report both in a table.
Okay, and then if you were typing out comparing, saying, sleep quality was a bigger predictor, its beta score was this, or compared to, yeah.
Absolutely. And what I would do is I would go to papers. You can even find papers that I have written regressions and copy the way that the reporting has been done for the regression, including the table.
Okay, yeah.
That's what I normally do.
Thank you.
No worries. Are there any other questions? All right, so this is what a multiple linear regression looks like. Remember we looked at the simple linear regression? Basically, a multiple regression kind of moves this baseline around a little bit. So the baseline depressive symptoms. Here is the slope for the BMI, if BMI was significant. Here's the slope for diet quality, and here's the slope for social connection. So multiple regression is almost identical to the simple one, but just with more slopes. And then you can use the formula by pumping in what someone's BMI is, what someone's diet quality score was, and what someone's social connection score was to predict what their depressive symptoms would be. So looking at the building of the model is interesting. So how do we decide which variables to combine and what order the blocks should go in? Is a really interesting question. And this decision has to be based on the literature, what you're hypothesizing in about your research question, and your own logic about what you've found in the past if you've done research before on this. There are so many different ways that you can build those blocks. I usually put demographic variables first, lifestyle factors second, and then my unique predictor last. But as Rhiannon said, when something like this happens, I could flip that model around to see putting diet quality first, then say lifestyle factors, then demographics, to see where we lost our significance. So it is okay to do that. And it's not p-hacking, it's exploring things in your data. Grouping variables if you don't have a good reason to investigate them separately, kind of like what we did today. So we grouped all of the lifestyle factors together instead of putting them separately in a block each. Don't group variables that are conceptually very different from each other. So like age, gender, socioeconomic status are different to the lifestyle factors that we looked at today. So we wouldn't put them in the same block together. Usually the least important predictors go first. So that's why I always put demographics first. And the variables that are at the center of your investigation go last. So whatever your research question is, whatever that predictor is, should always be in a block by itself. And you should always justify in your data analysis strategy in your method section how you built your model and why, justifying the reasons why it was built that way. So this is kind of what it would look like. You put your significant demographics in. It looks like marital status was, but we didn't check that. So marital status would have went in first, then sunlight exposure, social connection, sleep quality, and then diet quality in the final. Again, if you have questions about your own data and how the model should look, if you are doing a regression, feel free to email. These are the steps that we took. Our assumptions testing. So next time, we will be covering logistic regression, which is where if you wanted to look at different groups, so say we take our depression scale and we know that the cutoff score for depressive symptoms in the CDSD is 16. We could create a variable where everybody who scored less than 16 is in one group and everybody who was over 16, a score of 16 in a second group. We dichotomize our variable so it has two groups, depressive symptoms or not experiencing depressive symptoms, and then we can run a regression on the outcome variable when it has two groups instead of a continuous variable. Then we're going to look at ANOVAs. ANOVAs are like the t-tests that we did last week, where we looked in experimental research at the differences in the average of two groups, so healthy diet and unhealthy diet and depressive symptoms, and saw whether the mean score of depression was greater for the healthy diet or the unhealthy diet group, and whether that was significant. ANOVAs take that a next step when there's more than two groups. So say we had vegans, vegetarians, and omnivores, and we wanted to see what the depressive symptoms were across those three groups, we could run an ANOVA to see which of those had the highest average depressive symptoms. Then we're going to look at mediation and moderation. They are very helpful in a situation like what we found today, where depressive symptoms became non-significant because of either sleep quality or social connection. So we can see whether those are mediating the relationship or moderating the relationship between diet quality and depressive symptoms. So we will look at that next week. Are there any questions?
Any final questions for Megan before we wrap up?
Thank you.
Thanks, Oscar. All right, well done, Megan. That was excellent. So we'll be meeting up again next Wednesday, 2nd of April, for this final session, Advanced Statistics 2. So
Thank you so much.
excellent, Megan. Okay, thanks so much. See you then.
Bye.